Welcome to this chapter 6, linear regression with multiple regressors or multiple linear regression from Introduction to Econometrics by Stock and Watson. Chapter 6. Before I go to chapter 6, I am going to give a brief summary what we have been discussing in chapter 5 and 4. What was our policy question, that whether class size or student teacher ratio reduction will lead to improvement in test score. So no, there can be many other factors which are affecting both student teacher ratio as well as test score. In that case, if some variable is affecting student teacher ratio and test score and is not included in the model, it means this may lead to correlation between student teacher ratio and UI, which means expected value of u given x will not be equal to 0. So that's what we say omitted variable bias. Second thing is causality. So in general, an econometric model has 4 objectives. First is summarizing data. Second is forecasting analysis. Third is causal analysis. Fourth is policy analysis. On causality we'll talk in detail at some other stage. Multiple linear regression and estimating it by OLS. What is R square? What is adjusted R square? So we'll discuss adjusted R square. Why do we need adjusted R square? Why should not we rely solely on R square? Sampling distribution of the OLS estimator we have already discussed in chapter 4 and 5. That's more or less same. Omitted variable bias. When our omitted variable bias occur, there must be 2 conditions. First of all, a variable on the right hand side z, if that z variable is a determinant of y, and second condition is it is correlated with variables on the right hand side of the equation, that is it is related with x. Then if it is not included in the model, if it satisfies these 2 conditions and is not included in the model, this will lead to omitted variable bias. Please be careful. Many people will raise a question that if correlation between z and x is not equal to 0, there will be multicollinearity. Multicollinearity we shall also discuss in this chapter. Perfect multicollinearity, high multicollinearity, why does it occur? And I have also another video clip on multicollinearity. I'll give the link in this video. In the test score example, you see California. We are taking data from California, 420 districts, data used in Introduction to Econometrics, Stock and Watson. You can download that data. In general, there are many immigrants, particularly from Mexico. So they are non-native English speakers. What happens that grade 1, 2, 3 English language ability matters a lot in test score. So it means that English language ability affects your test score. Second, in general, who are in the immigrants have low income status, and classes where you have more percentage English learner students, their class size are large. So large class size are correlated with student teacher ratio. The English learner percentage and student teacher ratio are correlated. Where you have more English learner percentages, higher the English learner percentages, higher the student teacher ratio. So if these 2 conditions are satisfied and you have not included percentage English learners in your model, what will happen? That will be in U. Since it will be in U, so is x and z are correlated, but z is not included, z is in u, so x and u will be correlated, which means OLS will become biased. That what we have discussed in chapter 4, that xi minus mu ux. So if they are not correlated, it means sigma ux will not be equal to 0, and as a result, if you solve it, this is sigma x u sigma square x, and then you multiply it, divide it. So by little manipulation, this will be rho x u. If x and u are not correlated, expected value of beta 1 hat will not be equal to beta 1, so OLS estimator will be biased. So these two conditions, that it should be a determinant of y and it should be correlated with an existing regressor. If these two conditions are satisfied and you have ignored that variable from the model, this will lead to omitted variable bias. There are two more examples which I am going to cite here, given in the book, that parking space outside schools. More the number of students in schools, more parking space outside schools. But parking space has nothing to do with test score. So therefore, it is correlated with regressor, but it is not a determinant of y. Another example, timing of the test. At what time you are testing grade 1, grade 2, 3 students? If you are testing them in the morning, result will be different. In the afternoon, result will be different. Late afternoon, result will be different. But so it means it's a determinant of y. But since we have randomly assigned these students of having high class size, low class size, morning, evening, afternoon, so it's not correlated with large class size. So that condition is violated. So in these two examples, parking lot and timing of the test, these two are satisfying one condition but not the other. The first one. So therefore, if you exclude that variable, this will not lead to omitted variable bias. So in order to dig it out, that whether English learner percentage has a role to play when in large class size and small class size, we have formulated this table. This is for whole data. This is for whole data, and we find there is significant difference, 7.4 units, 4.04. This we have already discussed in chapter 5. No. Percentage of English learners when they are less than 2%. We see that class size, where the class size is small, percentage English learners are small, there are 76 schools, and there are 27 schools only where you have low percentage student teacher ratio and high class size. There are 61 schools where you have high percentage English learners and high class size. So as number of English percentage learner increase, student teacher ratio increase. So student teacher ratio and percentage English learners are correlated with each other. That we also find out later on, the correlation between English learner percentage and student teacher ratio. And obviously non-native English non-native English students will have slightly lower test score than native English native students. So therefore, it's a determinant of y, as well as it is correlated with the right hand side regressor. If you omit English learner percentage from the model, it may lead to omitted variable bias. So it's one more point here. You see, we have summarized this data, and this is a nice way to present summary and to get insight. But if you have a couple of more variables, then this table will become a mess. Therefore, regression analysis, econometric model is the best way to summarize your data. That is the first objective of doing regression modeling. So we don't go for this idealized random control trials at the moment. We come back to class size. In general, these idealized random control trials are not possible here, that we assign students randomly to small class size, large class size, as it's not permissible as well as not practical. So we have considered a variable percentage English learner, and we will do it in observational study. There are three ways to overcome omitted variable bias. There are three ways to deal with this omitted variable. First one is that we just assign students at random to small class size, large class size, medium class size. In that case, percentage student English learner will be a determinant of test score, but it will become uncorrelated with student teacher ratio because we have randomly assigned class size. Second case, as we have done it in table form, but when we have more than a couple of regressors, we'll run out of basically space, and there will be it will become very difficult to interpret those tables. The third and the most practical form is your regression table. So we use regression, and what is that regression? That is, you have x1, you have x2, y is your dependent variable, x1, x2 are independent variables, y, these are basically ith observation, I means, beta naught, beta 1, beta 2, these are the population parameters, ui is regression error or random effect of omitted variables. Anything systematic in ui must be part of the previous part. So yi is equal to beta naught plus beta 1 x1. Now you see, what do we say? Beta 1 is effect of x1 on y holding the effect of x2 constant. What does that mean? I'll also explain in detail. At the moment, what do we assume? That if we make small change in x, but there is no change in y, x2, and there will be change in y, so what will be the case? That effect before and after, this beta naught, beta naught, this is wrongly written. So this beta 1 x1 will cancel out, only we will be left with this one, and this will cancel out. So difference after minus before will be, and what do we say? Beta 1 is change in y due to change in x holding x2 constant, and similarly beta 2 is change in y due to change in x2 holding x1 constant. Beta 1 predicted value of y when x1 x2 equal to 0. So long as mathematics is concerned, it's okay, but please avoid interpreting beta naught. Minimizing sum of squares of residual, this process is the same as we have discussed in chapter 4. Just you have one more variable added. So if we estimate run test score on student teacher ratio, we say that class size reduction by 1 unit improves test score by 2.28 unit. But when we include percentage English learner, there is more than 100% decrease in the effect of student teacher ratio on test score. Therefore, we have to be careful. If we have not included a relevant variable in the model, its some effect is in u and some effect will come here. So therefore, percentage English learner, correlation between student teacher ratio and percentage English learner is 0.19, and you will see it is significant. So percentage English learner is correlated with student teacher ratio. If it is not included, it will be in u, and its some impact will be in student teacher ratio, some impact will be in u, and student teacher ratio and u will be correlated. This will lead to biasness, and the first condition that percentage English learners also affect test score, that's also because it is also significant. We'll see in a short while. So you see, these all variables are significant: student teacher ratio and percentage English learner. It means this is a significant variable, which this indicates that it is an important determinant of test score. So if you exclude it, it will lead to omitted variable bias because it is correlated with student teacher ratio and determinant of y. We have basically y observed data divided into two categories. systematic part plus unsystematic part. Systematic part, unsystematic part. So this is your systematic part. Anything systematic here must be pushed towards this systematic part. This UI must be random. That is the name of the game. That you always divide your observed value into two parts. One is your predicted. What is predictable? That is which is systematic. And anything which is random, that is unpredictable. So standard error of regression we have already discussed. Root mean square error, R square. We are going to explain adjusted R square. So standard error of regression will be same, except that now we have n minus k minus 1. K is number of regressors. Previously we have only single regressor, so we have used 1 over n minus 2. Root mean square error is divided by number of observations. There will be little difference between the two if n is very large. R square is explained sum of squares divided by total sum of squares. We know that total sum of squares is equal to explained sum of squares plus sum of squares of residuals. If you substitute here total sum of squares minus sum of squares of residual, you will have this one. So you see, whenever you will add more and more predictors, total sum of squares will remain same, because these are 420 test scores which will remain same. This will remain fixed, but when you will have more and more variables in y hat, this will have an increase, this will have a decrease. So whether that increase or decrease is significant, whether that variable is really relevant or not, since R square will definitely increase, because sum of squares of residuals will go down as number of predictors will go up. Therefore, it was considered that there should be some penalty factor on R square, and that penalty factor leads to development of adjusted R square. So when number of predictors k will increase, sum of squares of residuals will decrease, and number in this bracket will also increase, because numerator is fixed, k is increasing, so this denominator is becoming small. So therefore, as k will increase, this number will increase, this number will decrease. So it's not necessary that R square will adjusted R square will increase. Adjusted R square will be either equal or less than R square. So adjusted R square is 0.424, 0.426. If n is very large, there will be little difference between the two. Standard error, you see, when we have included percentage English learners, standard error was before that 18.6, now it is 14.5. So it means now you can estimate your equation with more precision, and residual size has decreased, because standard error of regression is roughly equal to the size of a residual at it measures spread around regression line. So these three assumptions as it is: expected value of u given x1, x2 equal to 0, x and y are IID, finite fourth moment. Another assumption, there should not be perfect multicollinearity. What is perfect multicollinearity? That your variable is linear combination of some other regressors. One regressor is a linear combination of another regressors. So these first three assumptions as it is, there is no perfect multicollinearity. If you include student-teacher ratio twice in your regression, what will be? So it means student-teacher ratio are perfectly correlated. This will lead to this will lead to collapse in regression, and student-teacher ratio will be dropped out. Please be with me in chapter 8. Then I will describe when we have here a variable and then its square. Many students question that there will be multicollinearity. No, that's not the case. Why it's not the case? Wait till chapter 8. Perfect multicollinearity. In general, perfect multicollinearity is due to some mistake. You have percentage English learners, you also measure it with fraction of English learners. You have added another variable more or less of the same nature in slightly different format. So therefore, whenever there is multicollinearity, you must find out which of these variables are collinear and which variable of these two can be dropped. When you have sampling distribution of OLS estimators, we don't discuss it a lot here. This is the same as normal distribution. Multicollinearity we discuss. That, for example, if you have student-teacher ratio less than 20, D equal to 1, and student-teacher ratio greater than 20, B equal to 1, now your B is basically 1 minus D, so there is perfect multicollinearity. So one dummy should be less than total number of categories. Why? Because intercept is always beta naught, x naught. X naught is always a variable of 1, 1, 1, 1, 1, 1, 1. If you include as many dummy variables as number of categories, their sum will be a column of ones. So intercept the x naught and those dummies will be perfectly correlated. That's why if we have quarterly data, we introduce 3 dummies. If we have gender, we introduce 1 dummy. If we have 6 states, we introduce 5 dummies. So 1 dummy should be less than total number of categories, or intercept should not be included. The other way around is, if you exclude intercept, then you should include as many dummy variables as number of categories. So this if you don't omit that one category, that means your system will collapse, and that is called dummy variable trap. Perfect multicollinearity, usually, as I mentioned, that it's usually a mistake in your data. When you have very high multicollinearity, as in lag variables, or if you have a close substitute, mango variety prices, orange variety prices, so then you can drop one variable, and it's up to you which variable you consider can be dropped, because it will not make much difference. Why multicollinearity is an issue? That's another issue. We have said that this is beta 1 is effect of change in y due to change in x1 holding the effect of x2 constant. No, you see, if x1 and x2 are highly correlated, then you cannot hold this constant and you can measure the impact of this. Therefore, there should be collinearity, as I mentioned, that x1 and x2 should be correlated, and if we have this one and this one is shared common portion, so we exclude x2 here, so this whole circle is excluded, and this is effect of x1 on y. But if they are highly correlated, then when x2 is excluded, basically x1 is left with very small part. That is also that's why we say that there should not be very high multicollinearity. Will be imprecisely estimated. Usually it's an error on your part, or some substitutes are there. Thank you for watching, and if you have any question, please post it below this video. I'll try to address the queries as per my best understanding. Thank you.